Introduction. My name is Christoph Pichler. Hi everybody. And today I'm talking about acoustic-based detection technique for identifying worn-out components in large-scale industrial machinery. So first, I want to start very low with a big iron production. So here in this picture, you can see a big iron production area in Linz in Austria. So in the left circle, you can see the blast furnace, which is running continuously. And this blast furnace gets loaded with iron ore and coke via such a huge conveying belt. And so also the raw material pre-processing is a very crucial step for big iron production. And what do I mean by raw material pre-processing? I mean that the raw material like ore, sinter, pellets, and coke get sieved and mixed. And this happens normally in such huge halls like you can see here on the right-hand side. And to show you how it is looking inside such a hall, I added this picture. So on the left picture, one can see inside such a hall, and on the left and on the right-hand side, you can see this huge vibrating sieves. And as I already told you, the smelting process is continuous, so it's also very crucial for the whole processing of the big iron, but also this pre-processing of the raw material should be continuous. Thus, a reduction of production shutdowns due to damaged wear parts of the sieves is needed. So we require a condition monitoring system. And since you have already seen these sieves are very huge and there are a lot of different sieves inside such a hall, it's very complicated to use conventional monitoring systems like vibrating sensors and so on. So, but we know that experienced personnel can hear faulty states with their ears. So we started by using an acoustic sound-based condition monitoring system to detect fault cases for such machines. Therefore, we designed a microphone array, which you can see here. So we put it up a microphone array with 8 measurement microphones and made it dust-proof because inside such a hall there is also a very huge dust load. So the basic idea is to equip the hall with microphones to monitor the sieves. And with such a data acquisition system, where we build it up here, we started to record the normal state in the hall. So the normal condition where there is no fault case. And you can see it here on the power spectral density analysis plot. On the left-hand side in red, there are some example measurements, and one can see that the overall frequency dependency is the same for the normal state, but the level is differing. And this different level are due to different operating states. And what do I mean by different operating states? So we have a lot of different sieves inside the hall, and these sieves can be now turned on or off. And so there are different combinations of different sieves turned on or off. So we have different operating states. Furthermore, we have additional interfering sounds inside such a hall, like signal horns or workers nearby. So we are not dealing with a unique normal signal. Our normal signal spans the whole signal space. So the normal state is a variable and a very complex sound mixture. It's very challenging to monitor the sieves in such an acoustic environment. And since fault cases happens in a yearly base, we did not have a lot of data for this. So we started to conduct fault tests. We did this with the assistance of experienced personnel. So a very common fault case is the rupture of a spring. And after the rupture, the spring hits continuously against the sieve. And we conducted the fault case by putting a metal plate against the sieve. And so we were able to gather data for simulated but authentic sounding fault cases. And here in the PSD analysis, one can see in blue the normal state of the hall right before we conducted the fault case. And in orange and green, you can see the PSD of the fault case, where in green there is the area marked where there is a level increase due to the fault case. But this level increase is way smaller than the level increase due to the different operating states. So the question was how to detect now such fault cases. And our approach was to use a so-called anomalous sound detection system, an ASD system. And the thing with that is, or the idea with that is, to overcome the lack of fault data. So the idea is to just learn the normal state and perform then outlier detection. For such a system, one needs for sure a data acquisition system, which I showed you already. And for the processing of the data, one has to first frame the data, then extract meaningful features to describe the data, and build up a so-called feature vector. The next step was to describe the probability distribution of this feature vector for the normal state. And we did it with a Gaussian mixture model. And by now, after the training class, after defining or describing this probability distribution for the normal state, we were able to perform outlier detection. So it is shown here in this picture, very schematically, just for 2 dimensions. Here you can see a probability distribution, and in green an inlier, and in red an outlier. So what we do, we describe the probability distribution for the normal state and perform outlier detection. And there are several questions which comes with that. So which features do we or should we need or should we use to describe the data? Which window length should we use to frame the data? And which Gaussian mixture model parameters should we use? So we started first by feature selection. We evaluated a lot of different features. What we did was calculate the feature value for the normal case and for the fault case. And we did receiver operating curve analysis for every feature, and used the best separable features for our feature vector to represent the data. And we were thinking about adding additional signal information to improve this method. So for example, we saw in the PSD that there is a level increase in a specific frequency band due to the fault case. So we also used band energies as features. And as I already told you, if there is a fault case, there is something hitting against the sieve, which ends up in a periodic knocking sound. So the idea was also to use the pitch information. Here in this table, there is a conclusion of the features which we used for our system. The next step was then to optimize the parameters. And what do I mean by parameters? First, I mean the number of components of the Gaussian mixture model and the optimal window length. And what we did was we first started with the window length, optimized the number of components for this specific window length. We evaluated it with a Bayesian information criterion, and then we used the optimized number of components and this starting window length, and performed again a ROC analysis. And we used the area under the curve as a valuation parameter. And we did this for several different window lengths, and you can see the results down here in this plot. And one can see that the optimal window length is at around or is at 18 milliseconds, which is exactly the period of the pitch, so the period of the sieve. And we found out that the optimal number of components to use is 4. So using the signal information, so the pitch improves this method by giving you the insight of the optimal window length. And now the question is, how does such an ASD approach perform for our specific application? So therefore, I used a test data set with 2,200 seconds of normal data and 460 seconds of fault data. And we performed, again, a receiver operating curve analysis. And on the left-hand side, one can see the results. And the area under the curve is quite high. It's 0.92. And we were able to calculate the true positive, or with such an approach, one is able to calculate the true positive rate and the false positive rate. And one can see that the false positive rate is here. There is a good separability between normal state and fault state, but for industry, 6% of a false positive rate is quite high. So here I'm also at the, let's say, at current work. So the idea is to also use the time information, because we are evaluating just the single frames. So always this 80 milliseconds. And by knowing that the fault case happens or is there as long as someone fixes it, we know that by adding the information about the time series, we can shrink the false positive rate. So, and then I come to the conclusion and the outlook. So I showed you that we are dealing with a very complex and variable sound environment, and that it's a challenge for acoustic sound-based condition monitoring systems, and that we are dealing with limited fault data. I showed you the importance of optimizing the parameters for such an ASD system, and we also found out that the pitch gives additional information about the optimal window length. The results show that such an ASD approach is an effective approach for such an application. And as I already mentioned, the idea for the near future is to use such a system as an online detection system. And we know that random events cause this false detection, so like the signal horn and this stuff. But we can reduce this false detection rate by considering the time series by means of maybe binary integration. Thank you for your attention, and I'm up for